Okay, so let's get started. So Marie-Lou Galprier is an assistant prof at Polytechnique in France. She works on, so I know you from, I guess, your work in understanding neural networks with statistical physics, and you're very interested in, Marie-Lou is very interested in kind of applying statistical physics to neural networks. And building new ML techniques for science. So today, she's going to talk about how to enhance MCMC sampling with machine learning. I really want to watch this talk, but I actually have to run and give a talk at the physics, ML physics workshop. So I can't, so I'm going to watch the recording. And then Natalie is going to come at the end. So your coffee break is at 3, but Natalie should be there before then. And if anything goes wrong, Christina is outside. Okay, thanks.
Thank you. Thank you very much for inviting me to give this lecture. Today we are going to talk about an aspect of machine learning, which I'm sure has been covered to some extent in the school before, but maybe not in depth, which is the power of machine learning to also model probabilistic models. So we are not anymore in the case where maybe we are doing classification or regression, but really we are trying to model distributions. So this will lead us to also consider generative modeling, which is really the tools in machine learning that has been developed to handle those things. And then we will see how we can go back and forth between those progress in machine learning to have generative models and what are the scientific needs in understanding high-dimensional probabilistic models. So maybe I should start with a small survey. So who's fluent to some extent with Monte Carlo, Markov chain Monte Carlo methods? Okay, amazing. This is why I'm here. And who is fluent in generative models? Much more, but not that much more actually. Okay, amazing. So I think the talk I prepared is at the right level, hopefully. And if you have any question at any point, do interrupt. So about the motivation, as I was saying, here we are going to be concerned with high-dimensional probabilistic models. So why should we care about high-dimensional probabilistic models? Well, they show up in many different aspects in science, and they are those big beasts that are quite difficult to approach. So where do they show up? So for example, in statistical mechanics or chemistry, what's our way of trying to understand the world is to have physical systems where we have an energy functional for those systems. So U of X describing the state of the system. And by Boltzmann distribution, by Boltzmann law, we know that the statistics of the different states of the system at equilibrium will follow the following density. So it means that we have, high energy configurations that will be much less likely, than low energy configurations and so on and so forth. So really, all this physics is encapsulated in this distribution. And if I can think of a concrete example to give you an idea, it might be, for example, that we are doing chemistry, we are interested in a molecule for a reason or another, and we know that this molecule can coexist in 2 different shapes, 2 different conformations. And we want to understand what are the statistical weights of the 2 different conformations. So in nature, do I expect to see maybe this one much more often than this one? And you can think, of course, of applications in terms of drugs. Okay, I know that this protein is active as a drug when it's in this conformation. How often can I expect it to be in this conformation and to be indeed useful? So that's an example. Now, if you are more into quantum mechanics, of course, you have the states of quantum mechanics that are intrinsically probabilistic and described by their wave functions. So here again, an instance where we have high-dimensional probabilistic models showing up. And then there are also some probabilistic models that are maybe not inherently given to us by nature, but some that we as scientists want to postulate, want to design, because we believe that they offer us a good way of understanding our data. And so that's what's going on in Bayesian statistical modeling. And the idea of Bayesian statistical modeling is that you will have some data, which is what I just put at this big D. And to explain this data, you will have a model. And this model will have parameters. That would be this theta. And you have maybe not enough data to decide that you can really settle for one model, for one value of the parameter. So instead, you are going to look at some type of distribution of how likely are your different parameters given the data that you observe. And you can, okay, I'm not going necessarily to enter right now in the details of all of this, but that's the idea of why we are designing those probabilistic models on the parameters of the models that we are designing as scientists, to try to have an idea of uncertainty in the model when we feed the data. So again, a quick little example. Here, it's coming from astrophysics. We have the radial velocity as a function of time of a star exoplanet system that we are observing. So I will have a picture actually about this later on if we get to the applications. But the idea is just that you have those measurements, those little black dots here and here, and you know that there is some type of periodic model that is explaining those measurements, which corresponds to some phenomenon of an exoplanet orbiting around a star. But you have so little data that you actually know that there are periodic signals with many different possible periods that are going to explain the data. And okay, having those this probabilistic view allows you to know, okay, so this one is likely, but this one also is likely. How much more one is likely? I mean, how much likelier is one from another, and so on and so forth. So those are all those probabilistic models, which in most cases, we know up to a normalization constant, which means that, for example, in the Boltzmann distribution, we know the value of this energy. So we know, if you want the value of this density, but we might not know the normalization constant because it's very costly to compute, although we know the value of the density up to the normalization constant. And okay, so that's one limitation, but you'll see that even if you know the normalization constant, those objects are very hard to probe. And why? Because when typically you have such a density, what you would be interested in is to compute the value of the expectation of some observable with respect to this density. So as I was explaining with the molecule model, you want to know the relative statistical weight between two conformations. So if you want the expectation of the time spent in the first conformation or the expectation of the time spent in the second conformation. So really what you want in order to make sense of those density, rho of x, of probabilities, is to compute expectations. Now you cannot compute those expectations because they include integrals over domains that are of very high dimension. Or actually, even if you are trying to ask your computer to compute maybe an integral over 5 dimensions, it will take quite some time, right? Because those computations scale exponentially in the dimension. So we cannot do it exactly. What's the method of choice? Monte Carlo methods. So how many people have heard about Monte Carlo? Most, right? Okay. So what's the idea behind Monte Carlo? Well, we know that there are ways where we can generate some realization of the random variable we are interested. So this random variable, again, could be the state of a physical model, or it could be values of parameters of some models if we were doing Bayesian statistics modeling. And such that we can approximate this expectation by an empirical average of those realizations. And so when is this equality true? Well, in particular, if x1, xn are what we call independent draws from the target density, right? Now, what's the problem? Okay, I moved from the computation of the integral to the sampling problem, but the sampling problem in itself has no simple solution per se if we are in anything larger than maybe 2 dimensions. So the next conceptual step is to actually be using Markov chain Monte Carlo, which have so this spirit of working by designing a transition kernel. So this is a probability to go to xt plus 1 when you are coming from xt, and to design it in a way that if you propagate this process for a sufficient amount of time, so start from x0, propagate, get x1 thanks to your kernel, and then from x1 get x2 from your kernel, and so on and so forth, such that after enough time, you will actually obtain sample from the distribution you're interested in. So it doesn't seem conceptually much simpler than getting directly draws from rho of x, but actually there are ways of designing Markov chain Monte Carlo that are, straightforward, that will allow you to have this property realized. Do you know of some Markov chain kernels? So, oops. Yeah, okay, so actually this is what the outline for today, and what we'll start with, let me just, is one of the hammer in Monte Carlo Markov chains, which is the Metropolis Hastings sampler. So what's the idea of the Metropolis Hastings sampler? Is that you are going to actually have, so this iteration, so this is the loop of the MCMC, and you will, initialize in some position, and then you will have 3 steps if you want. The first step is to have a proposition kernel. So that's this row index P for proposal to go to xt plus 1 when you come from xt. And this, in theory, you have freedom to choose, whatever. But it doesn't matter in a certain sense, I mean, on theory, what you take, because then you have this accept reject criteria, where what you're going to do is actually accept to go to xt plus 1 with a certain probability. And so this probability is going to put into the balance 2 different things. Both the what's the density in the target. So let's say that maybe I didn't write it down here, but now to avoid confusion, the target distribution will be denoted by rho star. So it will compare what's the statistical weight in rho star of where you are trying to go compared to where you used to be, the previous iteration, but also how it was likely for you to propose this jump. Because of course, if you are proposing this jump often, then you should not stay there too much because you will have an overrepresentation of the state. So if you, propose with a kernel, accept with a probability that follows this criteria, and if in case you reject, you stay where you are, you have this Metropolis Hastings sampler, which is going to converge to the target distribution under a few more assumptions, but it's if you want really versatile, you can apply it to anything. So it's really nice. Now, if we look at simple examples, here you can look at a 2-dimensional probability distribution that is going to have the following, if you want, contour lines. So what this picture means, right, is that here I have a high density region, here also, and here also, although they are a bit less dense. And here we have regions that are really quite not likely, right, when they are darker. And this 2-dimensional example that is called the Muller-Brown potential is usually used in chemistry to exemplify a bit the problems that we are going to discuss right now. So what's going to happen if I start my Metropolis Hastings sampler and if I use as a proposal distribution a Gaussian distribution? So here, yes, what this says, it says that if I am in xt, I'm going to take a Gaussian that is centered at xt and that has a certain covariance, and I'm going to try to jump somewhere in this Gaussian distribution. And then I accept and I reject according to the criteria we were just describing earlier. And if you do that, let's say for 100 steps, what's going to happen? Well, most likely you are going to converge towards a high density region, right? Because your samples are going to, I mean, they need to reflect the fact that rho star has a lot of density here. So just by the accept reject criteria, you will end up in a high density region, although you are really searching at random. So you can see that it's not really going the most direct way. Now, okay, this is really the Gaussian random walk, maybe the most basic Metropolis Hastings sampler we can think of. But what you can also do, for example, would be to use gradient information. So you know about the U star, if you want. This is the U that corresponds to the rho star you are trying to sample. So when you think again about this rho star as being exponential minus beta U. And so what you can do is when you use as a proposal, you stay in xt, but actually you also take a gradient step towards decreasing energy. And then you draw a Gaussian noise around this gradient step. And so if you apply this to the same picture, you can see that, okay, for some reason it went to another region of high density, what we call a mode. But what you can mostly notice is that it took, big steps in when the gradients were high, and it has somehow more purpose in finding the high density region. Okay, so this one we call the Metropolis adjusted Langevin algorithm because it borrows from Langevin dynamics, if some of you were familiar with that. But now what can we intuit is a problem with those MCMC? Does anyone of you have an idea? Well, now let's say, so same example, that I repeat this not for 100 steps, but for 10,000 steps. What has happened? Well, sure, we visited very well this high density region. But if I just look at the values of X from the statistics I get from the positions I was visited by this walker, well, I have no idea that anything interesting is going on here with those algorithms. They have those local transitions. And in cases where there is in the target distribution what we can call energy barriers, or if you want, those are the low density regions in between high density regions, then those local algorithms they will eventually transition, but you will not be here to see it, right? So problem of the correlation time. And what you could argue is that, okay, but here you see the step size, which means the variance of the Gaussian that I'm taking around the previous point to try to jump is maybe too small. So this is why I'm taking those little steps and I will never transition. Problem is that if I was to increase this step size, so this is what I'm increasing here, well, the number of acceptance I will get will just plummet. And why? Because it's just that I will be, maybe here, and then I will be shooting somewhere here. And so most of the time, I will be completely out of the high density regions. And even if I'm here and I'm sampling, proposal steps in something like here, okay, once in a while it will go here, but it's going to be so, it's so rare that most of the time I will just get stuck where I used to be, and I will just never decorrelate. So that's a major issue of those local Metropolis algorithms, and you can see that it's due to this locality, and those in particular those very challenging what we would call multimodal distributions. Okay, and of course what I've only presented to you was right now some algorithms that are very simple, really local, yet there are many more propositions in the literature that are trying to mix faster. So, for example, there are Hamiltonian Monte Carlo, which tries to exploit Hamiltonian dynamics to try to sample further. I mean, I'm not going to enter to the detail today, but there's also some much more intricate methods that are actually sampling different target distribution, which would be the equivalent of sampling distributions at much higher temperature and little by little decreasing the temperature, because we intuit that things at higher temperature are much easier to sample than at lower temperature. So that's what we call an annealing. And so this is something you can do, but that is also computationally very heavy. And that's so that's, I mean, sets the stage for what are our motivations and what is the main problem we are facing. Is there any question up to now? Yes?
Is the goal of this to find like the density of like the density distribution, or are you trying to also do like integral distribution?
Yeah, so the idea is that you want to find a way of obtaining samples from the distribution that are the closer as possible to being independently sampled from this distribution, which means that you should have, you know, many realizations here and a bit here and a bit more here and none maybe there, in such a way that then you can compute expectations. So you can approximate integrals. That's the whole game. And the problem is how to do that in general. Okay, yes.
What's the stopping criterion here? How many steps?
So the idea is that you should have a convergence criteria. You should have, well, okay, there's two things. There's how much you can afford to run, and there's also what are the good metrics to decide that your Markov chain has converged. So I'm not going to cover too much of that today, but you have different things. So for example, let's say you want to compute an expectation. You can, at each iteration of your chain, you can use all the samples you've seen and compute this expectation. If the value of this expectation is still changing as you add samples, you have not converged, right? So, you know, there are easy things that you should look at, like this for convergence. But also here, you see that what I'm just telling you is tricky, because if you look at the expectation you get, I mean, here your algorithm believes that there is just this big blob and it's very happy, right? So it's actually a question that is really complicated, and sampling high-dimensional distribution can become arbitrarily complicated, but that's a really good question.
So are you saying that the Langevin dynamics version avoids this of going into one well as opposed to exploring?
No, I mean that's
it also does that?
No, it also does that. I mean, yeah, you're right that it's a bit confusing, because in another talk I had put Langevin dynamics here because I didn't had discussed it at the previous slide. But yeah, you're right.
Okay.
Yeah. So sorry. So now I want to flash the. Oh, but I'm just going to put the outline because I didn't put it at the right place. Up. Share screen. Up. Share. Okay. So amazing. So, okay, there is a yellow box you're not seeing, but never mind. So okay, so that was the yes.
I was just wondering if you had like an estimate for the complexity of the Markov chain Monte Carlo methods versus like directly computing.
Yes, so so computing the integral is exponential to the dimension, right? And computing the Monte Carlo estimates actually doesn't depend on the dimension. So that's a big statement, because the idea is that you have a convergence that is going to actually be how should I say? Be driven by the number of samples you use. The variance and the estimator is really okay. Let me phrase it this way: the number of samples you need to make the estimation as a function of the dimension is actually not depending on the dimension. Yet there is a prefactor that depends on the dimension. And this is also something that you don't control because it depends on the problem. So it has to be as faster, just because you know that you don't have to have visited all positions, whereas in the integral you would have visited all positions. But depending on problems and depending on how you engineer your Markov chain, as we are going to see, those scalings can be really different. Okay, so the outline for the rest of the time we are going to discuss together is going to, okay, have a bit more, have a couple of more methods to tackle those problems of estimation in high dimension with probabilistic models. So after the Metropolis Hastings MCMC, and that's going to be variational inference and importance sampling. And once we will have this, we will go to these deep generative models and unsupervised learning, reviewing rapidly what they are and what they can do, and finally combining it all to try to have faster ways of precisely computing, estimating those expectations. Okay? So I had already covered the Metropolis Hastings. So let me go to the variational inference. So who has already heard about variational inference? Okay, amazing. So what's variational inference? Well, in this case, you're not really thinking about sampling anymore. What you're going to do is optimize a surrogate model to approach your target distribution. So let's say that your target distribution is this rho star. And that you have a parameterized distribution, rho theta, that you are going to adjust to match as closely as possible your target distribution. Well, the way you typically do that is by using this Kullback-Leibler divergence, which is a measure of how different two distributions are. And in particular, this is always going to be positive, and it's going to be 0 if and only if rho theta is equal to rho star. So you can see that it's a good, in a sense, training objective for your surrogate model rho theta. And you can actually evaluate it because it's an integral over rho theta of the log of the ratio between the two densities. But you see that this log, the expectation of this ratio can be approximated by a Monte Carlo method just by drawing from rho theta. And this is what you assume you can do easily. So that's the way people do variational inference. And for example, let's say that you, what are the examples of simple rho theta that you can use? So distribution that you will be able to write down the value of the density and to sample easily. Well, something that is ubiquitous is to use Gaussian approximation, right? So it would be a model with two parameters. Well, if it's in the dimension, then you will have a vector and a matrix parameter for the mean and for the covariance, right? Now, if we think, oh no, there is no okay, I'm missing a plot. But if we go back to, oh, here it is. So if we think about this distribution we were just mentioning, and if we think about the best Gaussian approximation to it, what do you think? So we have something that is a bit like this, right? Oops, that doesn't work. Yeah, there's some black. Better. Yeah, okay. So we have something that is a bit like this. And what's the shape of a Gaussian? Yeah, it's going to be an ellipse, right? So it's not even clear what it would be the best approximation. Maybe it will just actually catch one mode because this one has most density. So maybe it will just have a rho theta that is like this, or maybe it will try to do, a big Gaussian like this. But quite clearly, you have an issue when you are doing this variational inter, which you are, if you want, trusting your rho theta to make all the operations you didn't know how to do on your rho star, is that you have an issue of expressiveness or expressivity of the surrogate model. And you have to have an idea of how to control the quality, which you can do difficultly, because here actually, if you don't know the normalization of this rho star, in the end, you don't know where is the 0. You have a constant, this loss function up to a constant. And so it's not so clear how to control the quality. Because here it's in 2D, so you can check. But in 2D, you can do whatever you want. But we are thinking about, maybe 100 atoms molecules or 10 parameters models or things like this, so in higher dimension. Okay, so that's still something that has been really useful in many contexts, but you can see that it has those caveats. the third thing I wanted to mention here is importance sampling. So does that ring a bell? To some, yes, okay, to many. So just the quick reminder of importance sampling is that here we are going to have what we call a proposal distribution, rho P, that we can easily sample from. And then that we are going to use the samples from this distribution to compute weights that we are going to insert in our estimation of the expectations. And what are the values of those weights? Well, they are just precisely comparing what was the actual statistical weights of the sample xi in the target density compared to what it was when we have drawn it in the proposal density. And we have this that we renormalize by all the samples we've seen to get rid of the normalization constant we don't know. And by just this simple computation of those weights that we put in the estimation of the expectation of some function f we are interested in, we can do, have an estimate of expectation with respect to actually rho star. Now, let's consider a one-dimensional case in which maybe we have the target density that is this blue curve. So of course, this is easy, but imagine just the case we would like to do it with importance sampling. And imagine that the rho P density is this red curve. So what's going to happen is that we are going to have samples all the way here. And then when we are going to reweight them, the samples that were here and here are going to have weights going to 0, because in the target density, they don't really have density when they were here and when they were here. And so we are going to just reweight things that are really in the core, and things are going to work pretty fine. Now imagine we were doing it the other way around. Imagine that I propose with the blue density, and that I'm actually looking at, searching for an expectation with respect to the red density. What's going to happen? So I propose with the blue, while what I'm actually looking for is the rho stars that corresponds to the red. So the sum, yeah?
You won't see like the tails, right?
Yeah, you won't see the tails, right? Because here, the blue is going to give you samples that are here, but none here and none here. Or you would need to draw a massive amount of samples to start seeing, the very, very unlikely places that are here. And so, although if you would have a sample here, the weight will be big because the reweighting will realize that this place is unlikely in the proposal, but likely in the target. Well, if you do it this way, you probably will never see samples here. And so you will never have this power of approximation. So this is, you see just a picture in one dimension to give you the intuition. But of course, this is worse and worse as you increase dimensions. And if you want, this is the issue of correspondence between the target distribution and the proposal that we have in this importance sampling, right? We need to have precisely the density proposal that is a bit wider than the density we are actually after. But this can become really stringent in high dimension, because if you are a lot wider, it also means that you will draw all those samples that will have just 0 weight and that you will not be using at all. And so you will be using losing a lot of computation power at taking care of those samples that are actually not at all representative of your target distribution. So you have a problem of this correspondence. Yes?
Practice, how would you determine a proposal distribution? It seems like at least you need to know the mean.
Yeah, exactly. So importance sampling works out of the box, if you want, in low dimensions, because you can postulate something that is very flat, and you will manage. But in high dimension, importance sampling only works if it's adaptive, meaning that it's going to indeed try to look at samples and adapt the proposal to it. But we'll come back to adaptive methods. Okay? Okay, so that was the difference, inference and sampling methods I wanted to flash. Now, let's put them in face of what we can do now with generative modeling and unsupervised learning. So I don't know how much you are familiar with them, but I would phrase the paradigm of latent deep generative models as the following. So how do they work? They are those probabilistic models that start with a latent variable that I'm calling Z, and that is a random variable drawn from a simple distribution that I'm going to index by B because I think of it as the Bayes distribution. So I have this Z that comes from a simple Bayes distribution, think maybe a multivariate Gaussian, that is then going to be transformed with a parameterized transformation that I'm calling T theta. So again, theta always standing for the parameters. And in a way that's then when I transform, then I obtain this X that comes from this T theta of Z. I obtain samples from a distribution I'm interested in. So typically this T theta is parameterized by neural networks in many different ways. And typically what we do is that we adjust the value of the parameters of the transformation such that what we get as X's through this process is going to imitate what we have seen in training data. And for example, it's widely used in image models. And here the deep generative model I'm mentioning is is transforming Gaussian noise in images of dogs. Okay, and we can see them as probabilistic models parameterizing some type of rho theta of X that is highly flexible, right? So we can do things that are really efficient, right? And in particular, what you can notice is that they are able to, okay, no, this is not something I was going to say now. Okay, I'll come back to it. Do you know about, yes?
How much control do you have over the kinds of images that are produced in this way?
What do you mean by control?
Like let's say I wanted this picture of a dog, but I would have to pass through some Gaussian noise to get it, but I don't know how I would actually get the dog. I would have to maybe try a few different instantiations of Gaussian noise.
So it depends on what you train the model with. So let's say you train the model on a data set of different pictures of dogs. If it's well trained and people can do amazing things, then each time you draw a new random Gaussian noise, you get a new image of a dog. It will be different each time. I think there are some cases where they manage to reverse engineer the models to, for example, control for color or control for things. But just in this simple version, it's just you get a new noise, you get a new dog, and you don't have control to which dog you're gonna get. And if you had trained it on a data set that has many different categories, then you would not really have control on which category you get.
Okay.
Unless you engineer the thing more. Yeah. Okay. So do you know, have you heard about deep generative models and different ways of training them? Yes. So if I tell you that there's two main paradigms, the first one would be to do maximum likelihood. So what's maximum likelihood is to say, okay, I have my training data, those are those xi's. What I'm trying to maximize is the probability of observing the training data. And okay, I take the sum of the log of this probability for each of the data points. So that's the maximum likelihood framework, which is ubiquitous in unsupervised learning to learn probabilistic models precisely. So that's one paradigm. And the second paradigm, and of course, when you have the loss, then you just do SGD to find the value of the parameters, stochastic gradient descents. And then the second paradigm is adversarial training. So everybody has heard about adversarial training. So you have both this generator, which is my T theta, and this discriminator, D of phi, and you have this, what we call a min-max gain, where the generator is trying to fool the discriminator. The discriminator is trying to recognize whether a training data point was generated by the generator or comes directly from the training data. So it's trying to, fight against the generator that is trying to generate data that looks as well as closely as possible as the training. And the discriminator is like, okay, you don't fool me. I know what's from the training data, and I know what's from you. And you have this min-max game that's historically led to the first really impressive generations, for example, of images. So that was back in 2016, 2017, that this DC GAN could generate images of faces that were really convincing through this paradigm. Okay. Now, concerning this maximum likelihood, which is maybe more common in the general literature in machine learning and not in deep learning in particular, there is a caveat with many of these deep generative models. Do you have an idea? So if I tell you variational encoder, do you know about them? No? Okay, so the variational encoder, which I'm not going to review into the detail, but is trying to go around this problem. What is this problem? The problem is that I can not actually compute the likelihood of those models in general. So again, you have this process that defines this rho theta. And if you were to compute the value of this rho theta, actually what you would have to do is to compute a high dimensional integral. So why is that? It's because what you know about this rho theta is that you sampled something from rho b, and then you passed it through t theta. And so it means that it corresponds to the volume or the density, if you want, of all the z's according to rho b, which matches the x and the transformation with t theta. So with this delta function that is only going to contribute to the integral if those two are equal. So in the end, the way those things are defined actually doesn't give you an explicit formula for this rho theta. You will need to compute an integral, which is, we are back to the original problem of computing high dimensional integrals, which is not at all simple. So this is why actually there is what we call variational encoder, which are constructing variational approximation within the training. So, okay, this starts to become intricate, but that's what this is about. And this is the motivation for introducing a new type of deep generative model you may or may not have heard of, which are normalizing flows. So does normalizing flows ring a bell? Nope. Okay, so there are this specific type of deep generative models which are working exactly in the same way as I was describing, except that they impose a constraint, which is that t theta has to be an invertible map. So it means that, for example, if I'm looking at generating some images that corresponds to a certain dimensionality, now I need to consider base distribution latent variables that have the same dimensionality, and I need to parameterize this one-to-one mapping between the latent space and the output space. So, okay, and if we have this t theta that is invertible, then we can compute exactly this rho theta. And that comes from what's called in the probability literature, the change of variable formula, where you just, okay, if you want, make the counts of who in the latent space will contribute to X. So you have to look at what was actually the I don't know how to say that in English, l'antécédent. what could have generated X. So you just take the inverse of X through the transformation, and you put that in the base distribution. And there is also a term that comes from the Jacobian of the transformation. I mean, no worries. You don't need to understand that into the details if that doesn't talk to you, but just what you need to have understood is that thanks to imposing the fact that the map has to be invertible, then you can actually compute the value of the push forward. And you'll see that this is what's super valuable in this business of using generative models for Monte Carlo methods. So, okay.
What's the latent space? It's not the noisy, the Gaussian noisy, right?
Yeah, yes.
It is?
Yes.
Okay.
You can still have a latent space that is a Gaussian noise, and you can still transform it with an invertible transformation in the image of a dog.
Why do I want to Gaussian noise.
You don't necessarily want to recover Gaussian noise, but you want to be able to evaluate that. And you'll see why in a second. Okay? But okay, maybe just to give you an idea of how we can parameterize neural networks to be invertible, because if you think about it rapidly, you will see that a typical fully connected layer is not invertible. A typical convolutional layer is not invertible. So how do we have expressive transformations that are invertible? Well, there's zillions of tricks. I think the number of tricks scales as the size of the community, and so in machine learning, you always get a lot of them. A lot of people are really good ideas, but the one in a sense I prefer because it's super easy, actually really expressive, so really neat, is the one of coupling layers. So what's a coupling layer? A coupling layer works as follows. So here you should think of X as being the input of my layer and Y being the output of my layer. And what I'm going to do is I'm going to partition the vector X of input in two things, something that I call X1 and something that I call X2. So you just imagine you have a d-dimensional vector, you take the d/2 first coordinates and the d/2 second coordinates, and you call them X1 and X2. Okay? That what you're going to do is you don't change X2, you just send it to the next layer and change. Y2 is equal to X2. But then what you do with X1 is that you have some invertible transformation. And here, actually, you can even do it with something very simple, like an affine transformation of X1, for which actually you computed the scaling, the scaling of the affine transform and the translation in the affine transform as a function of X2. So here, let's say that I have a X1 that is of dimension d/2. I have here a fully connected neural network that takes as inputs a d/2 vector, and that outputs a d/2 vector that I will multiply element-wise to X1. And here I have a transform that is also going to output me one scalar per dimension. And you see that if I do that, I can very easily inverse the layer, because I know that Y2 is equal to X2. So I can reuse my parameterized transformation, so typically with neural networks, to recompute the scaling and the translation, and just to inverse the transformation I did on X1. So with this coupling layer, which seemingly looks linear, but it's not, because it's linear, yes, in X2, but it's not linear in X1, because it multiplied things that took as input X2 and to X1. You can get things that are very expressive. And of course, you will compose those layers, right? So you will have, first you change X1, and then on the next layer, you're going to change X2, and so on and so forth, to get something that is pretty expressive. And you can also notice that if you were to compute the Jacobian, so which are the coordinate-wise derivative of the map that you need in the change of variable formula, this is also a layer that is very easy in terms of computing this quantity. So normalizing flows are easy to sample and easy to evaluate densities. And if I just, again, fix the ideas, by composing those different layers that seemingly are by themselves not doing much, we are going to be able to transform deeply distributions that we are interested in. So for example, if you take here this two-dimensional problem where I start from a Gaussian distribution in 2 dimensions, and I just color the points according to their coordinates on one of the axes, just so that I can see where they are going to be moved by the network as I compose the different layers. And I show you where the different points are going after different layers. If my target was this distribution that has the shape of a cross as the density, you can see that little by little, this is going to get you closer and closer to something that becomes more and more complicated. So, of course, this is still very simple, But trust me that you can do things that are really elaborate with those networks.
Have the non-linearities between the layers.
You could have nonlinearities that are invertible. That wouldn't break the principle. But I haven't even been needing to use them. Because, I mean, just the fact that here you have nonlinearities is enough. Okay? Question? No? Okay, so now that we have those big deep generative models, and that seemingly each time I generate a new Gaussian noise, I can get a new sample from a complicated distribution, such as a distribution that would generate dogs. What I'm asking myself is, can I use them? Can I use them as surrogate models to do sampling in high dimension, right? Because they are probabilistic, they sample very efficiently complex distribution. How do I make that bridge to obtaining the samples of this rho star that I may be interested in because it comes from my physics model or it comes from my Bayesian statistical model? Well, two things that should come to mind right up front is the fact that, well, don't you need data in order to train deep generative models? So if I wanted to have a generative model such that the rho theta is close to the rho star, well, I would need samples, data. The training data would be samples from the targets. That's what I'm after. So how do I break this conundrum? And second, even if I'm moderately successful at getting the generative model to train towards rho star, it's unlikely to be perfect, right? It's unlikely that I have rho theta that is going to be exactly equal to rho star. But as scientists, we care. We care about the fact that we are actually sampling from the distribution that we are after, right? It's a bit different from trying to sample images of dogs and being happy if more or less they look like images of dogs. We want to sample from the target distribution. So how do we leverage learning while knowing that we have no guarantees about how well it can learn? So that's time to come to the third part of the talk that is really going to put everything into places by combining traditional inference methods and learning. Any questions? Nope. Okay, so first we'll go back to variational inference and sampling. Then we'll talk about the opportunity of using normalizing flows as reparameterization map, adaptive algorithm, which we'll see how well we are doing on time, but this is where I've been working myself recently, so probably I'll spend too much time here. And finally, I mean, making just one, oops, there is a problem of numeration, but that's about this one last comment I want to make about incorporating more physics in the models and in the generative models. Okay, so the first idea that people had when they developed normalizing flows, and this idea was exploited in 2015, is to do variational inference with a normalizing flow. So now I have still this same objective that I want to minimize this Kullback-Leibler divergence between the target and the model, which I can efficiently estimate thanks to the flow, which is easy to sample. It's one of these deep generative models where you can just sample Gaussian noise and push it through the transformation. That's even cheap in your computer. Now, with the flows, you have also solved the problem of, okay, do I have an explicit expression for this rho theta? Yes, you have, thanks to the change of variable formula. And of course, now you have something that is much more flexible. So what are, for example, the Gaussian example I was describing to you at the beginning with normalizing flows. So in 2015, this is, for example, the first little time models they were looking at. So they have these two-dimensional densities that are their targets. So this is their rho stars. And they made those little plots that I like because it really exemplifies the problem of the expressivity. So here between the different columns, you have more and more layers in the normalizing flow, which means that your ansatz, your parametric model is more and more expressive. And you can see that the result of the variational inference, so the rho theta that they get, is going to become better and better in the sense that it's closer and closer to the target as you add more and more flexibility to your model, right? So that was back in 2015. Now in 2019, the team of Panzang wrote this paper that was called Solving Statistical Mechanics using Variational Autoregressive Networks. And I would say that the key problem in statistical mechanics is computing free energies. And this is precisely what they did, computing free energies, which corresponds to the normalization constant of the Boltzmann distribution. And they did that so for a spin system that had 20 spins. So the dimension starts to scale up, right? This was two-dimensional. Now we are looking at a system that has 20 dimensions. And and they compute this free energy as a function of the temperature. So the shape is not so important, but what they did was compare it with different ansatz, different parametric models. So naive mean field being something really crude, and then up to using the normalizing flow, which are those red dots. And with the normalizing flow, they could get something that perfectly matched the exact free energy that's in the models they chose, they were able to compute. So that was pretty exciting. There was one caveat, which is that they required annealing of the target distribution. So what this meant is that actually they were not directly after their targets. What they had to do is engineer this scheme that first they will fit the equivalent of the target density at higher temperature and little by little decrease the temperature. So there was more tricks going on. So again, why? And it boils back also to the problem of how do you control the quality of the surrogate model that you train. And to show you what can go wrong and why in that case they need the annealing, let me show you this really simple example in 2 dimensions again, where the target would be this mixture of Gaussian, which has 2 modes, right? 2 components in the mixture of Gaussian. One of them is twice as likely as the other one. Okay, but that's something you would like to sample from. Now let's imagine that you run the variational inference as we have stated it with these targets. And here in blue, what I'm plotting is the value of this rho theta. So I'm going to launch the animation, but right now it's just at the beginning of the learning where it doesn't know anything about the target. The initialization was random and it's here. And what's going to happen in this case, if I launch the movie, is the following. Again, what's happening is that I'm just plotting what's going on to rho theta of t if I'm running a gradient descent on this objective function to try to have rho theta come closer to rho star. So what has happened? Yeah, so it flew to one mode. It even concentrated all the mass of rho theta at the center of one mode. It has no way of knowing that something else is happening somewhere else in the space because it gets all its information from where the model has data. So that's, if I manage to relaunch the animation, that's what I was figuring out with those little dots that correspond to the sample you are getting in order to evaluate your loss. They don't explore at all the whole space. They only explore where there is some blue. And so it's just going to flow towards the closest mode and cannot do anything better. So that's what we call mode collapse. And that's a problem of this objective when doing variational inference. And here, there's the problem also that you will not know, right? Your loss will decrease and you will be very happy. But if you have no idea, then that something else exists somewhere, you will never know. And that's a fundamental problem about finding modes in high dimension, which, we know can be arbitrarily difficult. Okay, so that was a first idea of how to use this new technology in order to accelerate inference. The next idea was to use it for importance sampling. And here in this paper that made a lot of noise that was called the Boltzmann generator by the team of Frank Noe, and that appeared in Science in 2019. They actually used maybe two things. Okay, they made two innovations, if you want, compared to the variational approach I was just showing you. First, in the training scheme. So what they did is that, okay, they did use the same variational inference loss. So that's exactly what we were discussing. But they also added some data. They assumed that they had some initial data, so some initial samples that were representative of the distribution. They were trying to sample further. And so they could add a maximum likelihood term in their loss. So they combined the variational inference with something that you would do if you had a training set, making the assumption. And in their case, they were looking at molecules, so their data were coming from molecular dynamics simulations. So they did that, and what they also did was to phrase it as importance sampling. So with importance sampling, what you can do is, again, sample from the flow, and then correct for what the flow has learned by reweighting according to the target distribution, which, again, you know. So you're able to compute this reweighting and plug those weighted samples in the expectation of any function you want to estimate. And so doing this, they were relatively successful. And in particular, they were able to look at proteins with 58 amino acids. So, you know, dimensions are starting to scale up and up. Again, by having this combination of a surrogate model, that this is the picture of a normalizing flow that generates from a Gaussian and then generates some molecules, and then having this control with the reweighting. So in particular, if your model is completely off, you will see it because all your weights, all those ratios here would look really tiny. Or you will have a high variance of those weights. Yes?
For sampling in general, do people usually only care about getting the mean of the function of the distribution, or are there other?
So here we are being, you know, somehow vague because we use this f as the function we want to estimate. But for example, if you, f could be the identity, and then you look at the mean of the distribution, or it could be a square and it's a variance, or it could be the energy functional and you're looking for the mean energy. It could be whatever, okay. Right? Okay, so another problem that was in this paper, and I'm saying a problem, but another thing you should notice, because it's still a very impressive paper that managed to do a lot, is the fact that there was this chicken and egg problem between the fact that you need data in order to train your model that you want to train to obtain data. So there is this loop of, okay, you need to, if you want, nucleate the process with data in order to get the model to get data. So sure, and in a sense, it's not clear from this formulation how much data you need. So the next, okay, I will come back to this. And so right now, we've seen how to use normalizing flows for variational inference and importance sampling. Now comes what I started to tell you about, was the Monte Carlo methods and Markov chain Monte Carlo methods. So one of the first things that was exploited with the normalizing flow and the MCMC was the following observation. The observation that, again, I had this, you know, this little picture that I was just showing you, that you are able to map a Gaussian distribution to the output distribution that you'd like. And since the transformation is invertible, it also means that you can map the distribution you'd like to a Gaussian distribution. And the fact that you can have this, what we can call a reparameterization trick, makes it that you, instead of thinking of sampling the distribution that may have a complex geometry, you can try to transport your problem in the latent space and sample something that should be close to a Gaussian once your transformation is learned. So here, it was, so I think these two papers investigated this. So it was Boltzmann generated paper I just mentioned, but also the paper by Matt Hoffman and collaborators that was called Neutralizing Bad Geometry, with a pun on the fact that they were using neural networks to make this reparametrization. And here, this plot from the Frank Noe paper shows if we were reconsidering this molar potential in 2D, and if we are coloring samples that would be in this blob in blue, in this blob in orange, and in this blob in red, if we transport them back to the latent space, so applying, if you want, t theta minus 1, where they lie. So here, the latent space as the base distribution of a Gaussian. So they were mapping the Gaussian samples towards samples that would lie here. So if you take samples that would lie here and map it back to the latent space, you get something that is approximately Gaussian. And you can see that the samples that were in different modes somehow far away and separated here looks like they're close to one another. And so that you can exploit this reparametrization to actually think about doing the MCMC in the latent space. Yes.
Why do you need to do RCS?
Excellent question. So in the next okay, so in the next method I'm going to show you, we are actually going to directly sample from the Gaussian. Now there is reason to believe that because of scaling problems that I will hopefully tell you about at the very end, doing something that is still local would make sense in the latent space. Yes.
So does that mean the normalizer will is not learn the current distribution?
So let's okay, it only learns it up to something, right? And that's the problem, that you have this gap between what the normalizing flow can learn and what's the actual distribution that is going to become harder and harder to fill this gap as the dimension grows. Okay, but I'm also very happy to discuss that in more detail offline. But yes, you're totally right. So, but let me show you the next part, because I think it's really informative. So here, still on this idea of using what you've learned, the flow that you've learned for reparametrization, I just want to, place back the idea that if you had, again, a multimodal Gaussian targets, and if you were to do something that was purely local, then, a worker that was initialized in any of the modes would explore very well any of the modes, but there wouldn't be any mixing in between the modes. And in particular, here in this case, where there's one mode that is twice as likely as the other one, the data that you would look at, from these two workers, is not showing you that at all. You have visited the two modes with an equal number of times, and you cannot make sense of this. Here, where you are using instead the transported local algorithm. So here, what you have is, okay, it's not exactly the same target distribution, but the target distribution is a Gaussian with 4 modes. And here, what I'm showing you are the chains, one MCMC chain that comes from running this actually local algorithm in the latent space. And here, what I'm showing you in the latent space is the transport of these 4 modes by the T-1 transformation. And so what you can see is that the flow was trained to train a Gaussian unimodal to those 4 different modes. So if I just take those 4 different modes and I put them back, okay, this is not exactly a Gaussian at all, but you can see that it concentrated the mass in one place. And so the local algorithm here that is going on this weird landscape, but that is more compact, if you want, than the direct distribution, is going to be able to transition between the different regions. And you will, if you just transport back the chain in the direct space, what you will see is a mixing between the different modes. Okay, so the idea is just that we had those blue blobs as a target. We had learned a flow to map a Gaussian to those blue blobs. So then we can take the inverse of the flow to map the blue blobs to the latent space and run some MCMC that is local. but that is going to benefit from the reparametrization of the space in order to generate transition in between the modes. Okay? So that's a reparametrization trick. And anytime that you are trying to sample something that is not even necessarily multimodal, but something that, for example, would be very elongated in one direction and not in another one, just rescaling things can be really helpful. And that's what's being exploited. Okay. Now, fourth idea is to do things in direct space, and it goes back precisely to what you were saying, that you could directly sample from the flow independently, and that's doing adaptive MCMC. And that's something I've been working on. So what the idea of an adaptive MCMC is that you are going to adjust the way you do your MCMC along the MCMC using the value of the states you've been visiting. So in this instance, it goes this way, that you have your MCMC loop with the Metropolis Hastings algorithm we started with, which again has, the small difference here is that you need to think about it as having multiple walkers walking in parallel, so having multiple MCMC chains propagating in parallel. And then what's happening? Well, that you have, okay, the Metropolis Hastings steps, which uses as a proposal a normalizing flow. And this normalizing flow, which is a proposal that is no longer local in the sense that it doesn't depend on xt. You propose xt plus 1 completely independently of xt. And then you have your usual, computation of the acceptance ratio that is supposed to correct for how different is the proposal compared to your target distribution rho star. So you do that, and as you do that, things are supposed to get better and better. You're supposed to get samples that will look more and more like samples from rho star. And okay, and maybe you can do some local resampling that I will probably briefly mention. But importantly, what you also do is that you use the value of the xt's, so the value of all the states that you visit, in order to do some maximum likelihood training on the normalizing flow. So what you are using is the fact that the samples are going to converge to samples of rho star, and use them in order to increment the values of the parameters of the normalizing flows so that it approaches the values of rho star. Yes?
How does this, with the fact that still the Metropolis Hastings is still very local in the sense that the chain itself sees only goes to one mode. So how does this?
So that's precisely not what is going to happen here, because the proposal that we are going to use is non-local anymore. So you're somewhere in some mode, but if your flow has learned math on different modes, it will propose randomly in different modes.
But okay, so you begin with some flow that starts as something that is pretty local.
So let's look at this example. So this was just the same target local methods that I was just showing you. Now, and I will take your question maybe after the, right? So now this is what this algorithm would do. So I have a flow that has the same initialization as I was showing you before. It doesn't know about the targets, but I have walkers in each of the modes that are at initialization. And so the walkers are going to start walking. And as they walk, they generate data. And this data drives the learning of my flow towards the regions where there is data. And little by little, the flow is really going to learn what's the target distribution and is going to be able to propose samples in a location in two modes completely independently. So you will have really the chains going back and forth. And importantly, you will see that, okay, the second mode that was twice as likely will indeed be will indeed have a weight that corresponds to twice the weight of the other one. So here in particular in the normalizing flow, but most importantly, in the samples that you are going to collect, because they are corrected by this Metropolis Hastings step. So even if the flow was not perfect, the Metropolis Hastings step is correcting for it, but the fact that the flow is really good makes it really fast to equilibrate the MCMC chain. Question?
Yeah, this is really cool. So I was wondering why so the flow you can also train directly on the energy, right? But
That's-
you don't seem to do that here.
Because you have mode collapse.
Okay, but you cannot, I see.
That's the reason why. And you see, and this is why the other paper was using a bit of variational inference, which is training on the energy and some data. And here you are a bit, if you want, and here you could add the variational inference loss, but I think really the maximum likelihood loss, which you can access thanks to the fact that you are thinking about it adaptively, that you are using the MCMC samples to train yourself, is, I think, the most important in making this successful.
Do you know about the stochastic normalized flow paper?
Yes.
Do you know how that compares to this?
So you're saying the one from Frank Noe's group. Yeah. So the problem of the, I'm maybe being too vocal, but something that is a bit hidden, I would say, in this paper is the fact that they cannot compute exactly this rho theta anymore because they are putting some MCMC steps in between the layers. So they argue that you can do some Monte Carlo to estimate the rho theta, but you are starting to incorporate more and more approximations. So I think it depends on the use case. You're welcome. And to say, I think that goes back to your question of, well, how will the model know about the different modes? Well, it's because you pose it as a requirement that you initialize walkers in different locations that are of interest. And because if not, then you will never learn about them.
Just to make sure if you don't, the first animation, you put them actually in the modes of that. I'm guessing that in most practical applications, you won't actually know where the modes or even points that you think are special might not actually be like take the whole space into account. So you want to.
Okay, so there's two different things. There's the fact that here you're not actually sensible exactly where it is, but it has to be somewhere of interest within some of the regions you want to probe. But then that's realistic. For example, if you think about this molecular problem I was telling you about, you have those two molecules, you know them, but what you don't know is what's the relative statistical weights of the different conformation. Because maybe one has a much higher energy as the other one, but maybe it has a much more basin it can explore around it. And so its free energy is going to be much higher than the other one that has a lower energy. So that's the type of questions you want to answer to. And then if you don't know, and I mean, if you take just an arbitrary distribution in an arbitrary dimension, then we know it's NP hard to find local minimum, which means that it's just proven that it's a priori exponentially difficult. So here there is, if you want, no mode discovery, and we don't claim that we are discovering mode. What we claim is that if you have some vague knowledge of where you are interested in, you'll be fine.
And this can actually be used with any proposal distribution like something, not just in
Yeah. You can any proposal-based MCMC can take advantage of this. Okay. What was next? Yeah, it was just a picture again of saying that you have those chains that are propagating, and you are using the data from time to time of those chains to train the model that you are using in your non-local sampler, and that's just rephrasing the idea of the algorithm. And okay, and so I've been working on that, so blending in normalizing flows, but this adaptive MCMC is not at all something new. It's been, people have been thinking about it for decades now. It started with, okay, I'll do a Gaussian random walk and I'll adjust the covariance of my proposal to the data I've been visiting. And now we have those new, fancy versions where we incorporate generative models in the adaptive methods. But it also has a taste of local plus mode jumping methods, where you think about this, something that will allow you to explore a mode and something that will allow you to jump out of a mode. And regarding this, maybe something I haven't been insisting on is the fact that I'm also using a local sampler. So I'm taking steps of the non-local sampler with normalizing flow, but also steps with the local sampler. Any guess why?
So you have to explore some of it.
Yeah, it's good for the start, but even it's good all the time, because what you can be pretty sure about is that your normalizing flow is going to be really bad in the tails of the distribution. So the tail of the distribution is something that statistically you will see very rarely. And so your learning is very likely to be very poor. And here I just made up this little example. Okay, so I'm sorry, the projector is not perfect, but okay, the idea is that I have those two wiggles. Okay, it's an arbitrary choice, right? But imagine this is your target distribution. And imagine that you have a normalizing flow with a small representative power, and all that it managed to learn from it was those two blobs. So it has this proposal distribution with those two blobs. And if you want, it's just a toy model for the case where we are in very high dimension. We're thinking of very complicated distribution. And the flow will have learned something useful, but it will be missing on something. So here it will be missing the fact that there are some tails here that are coming out of the blob where it's proposing. And if you are using, if you are using only the global method, then what it's going to do is, okay, it's going back and forth from the modes. It's exploring well the realm in which it's proposing, but it's not at all going outside. Or when it's going outside, it's getting stuck. So here, the size of the dots corresponds to the number of consecutive rejection you got in the metropolis A sting. And here, when it's the global only, what it's going to do is say, okay, oh, wait, there's mass here. My proposal distribution is as very low mass here. I should stay for a while and not jump out. But it means that you will just stay in one point. And so the variance, I mean, your exploration is pretty bad. Compared to what's going on, if you're adding some local steps, is that, okay, the global metropolis A sting is not going to jump back because it's not favorable. It realizes that it's unlikely it will propose there, so it will stay there. But the local algorithm is going to make the job at looking around.
So how is this incorporated? Is it like one step with the global, one step?
Yeah, I mean, you can, I mean, the idea is to interleave them. Maybe you take 10 steps of the local, 1 step of the global. It depends on how much both of them cost you, right?
So, but it is interleaving. I mean, it's not something like every step to do something that takes into account both.
No, I mean, you can actually, you have pretty much freedom in phrasing how you want to do it. Yeah, but I think the simplest way is really interleaving. Yes. So, okay. So, I mean, there is this, what I call this exploration exploitation compromise. And you can also see it as the fact that the local kernel is going to compensate for the mismatch between your proposal and your targets. So I was telling you the flows, they're amazing. They're so flexible. You can do many different things, but still you cannot expect that they're going to do all of the job. And so this is why, in a sense, you should beware. You cannot learn it all. And also traditional local kernels are still of great help. And it's more about combining forces than replacing one by the other. Okay, what was next? Yeah, I got there to the adaptive algorithms. And then, okay, I'm sorry, I guess. And then do I have these slides on incorporating more physics? Okay, I have also examples, but maybe I don't have so much time. So I will just let you know about one quick example, which was, again, this problem of Bayesian inference. So let's say that we are here and we're observing this exoplanet, which we don't exactly observe. What we actually see is the star of this exoplanet. And because there's the exoplanet, they're actually orbiting the center of mass of the system. So from us, what we see are snapshots of the radial velocity along the orbits. So I simplified things. So I'm sorry if any astronomer is in the, is in the audience. But the simplest way of looking at it is that you have a radial velocity that is a periodic signal that has something like this. And you have observations at some given time of this radial velocity. And so maybe those observations were created by these models, which correspond to a certain value of the parameters. So parameters being some offset, some amplitude, some period, some phase. But what you can also realize is that actually, if I look at all the gray lines here, they could also be convincingly explaining the red dots, right? So this means that in the end, with my 4 parameters, oops, sorry, I thought there was something else. With my 4 parameters here, I could have other values that would explain the models. And so we can frame a Bayesian inference problem out of it that will have a multimodal posterior distribution. So multiple values, different values of the parameters, and in particular, you can see different values of the periods would explain the data. And so it's a relative, oops, okay, there's a problem in the order of the slides that I didn't see. Oops, where is this? I apologize. Okay. Okay, and so here what if you look at the posterior that this problem is defining, you will see, so here in the 2-dimensional projection with the logarithm of the period and the phase, that you have different locations in these 2D planes that have parameters values that explain the data. And the problem is, how do you estimate actually those different places? Because of course here it's a Bridges side problem. In theory, it has many parameters. And so we've shown that it was possible to learn this problem with the normalizing flow. And in particular, what you can see when you are launching the algorithm and you look at the number of iterations, that you have an acceptance rate that is going to go up, meaning that your normalizing flow is going to get better and better at mimicking your target distribution. And again, this acceptance rate is going to give you the fast transitions between the different modes. And here we could check that indeed we were able to equilibrate really efficiently this problem. So, okay, and just to finish with remarks, since the time is almost up, is if we look at scaling to larger and larger system, those problems, because that's definitely something we should care about, there is this issue that goes back also to something you were asking, although I'm not sure I can make it clear in a few minutes. You can come ask me afterwards. That when we are computing this Metropolis Hastings acceptance ratio, and it will be also the case, for example, for the importance weights, we can rephrase it this way, where we have this exponential of minus differences between energies. So the target energies and what we could think about the energies of the normalizing flow. And here, okay, this you have no control over, but this, so whether or not this delta U theta is going to be close enough to this delta U star, such that this is not always 0, is not at all trivial if you start increasing and increasing dimension. If you imagine that, okay, you're looking at a physical system, usually the energy is extensive, so it will scale as the number of particles or the number of dimensions you are interested in, then probably you are going to make an error in learning it that is going to be about this order. And if you start having an error that is of this order, it means that you will have exponential to n. And so this is something that is likely to go wrong just as is. So this is things that we are currently thinking about in adapting those things. And there was one paper that was in particularly exemplifying it. So it was on a statistical physics model that is called the 5-4 model. But I mean, it's not so important, but just they were looking at larger and larger models, and they were tracking what's the value of this acceptance rates in their Metropolis Hastings, basically using something like I was showing you. And what they could see is that as the model was getting larger and larger, the acceptance would plummet, and in particular at the position where this model has a phase transition, because this was as a function of temperature. So you can see that there are still things to be solved about applying these methods. And the important takeaway is indeed that's okay, but that's sorry. I will manage. Up and so up. Here we are. And so the important takeaways are that we can say that there are some great opportunities in applying those deep generative modeling methods to try to speed up inference and Monte Carlo methods, and with substantial speed up gains. But we can also see that there are challenges that are going to come for us. And that's one idea that we have in order to tackle those challenges is to have models that are going to be more and more informed by the physics. So the fact that we constrain the models maybe to have the symmetries of the problems we are interested in. For example, here, some papers were occupied about building normalizing flows that will have the geometries of torus or spheres, because those are things that people care about in physics, are really important. But there are many different ways in which you can try to physically condition a model. There is also some ideas of how to reduce dimensionality and still build on that for Monte Carlo methods, separation of scales. And finally, if you're curious about looking into algorithms, I have a couple of implementations that are up online, depending on whether you are PyTorch fans or JAX fans, you can look them up. And I mean, this one was more directed towards, just showcasing the first experiments. But this one is meant to become a full-blown package. So if you want to, have a look and make feedback, we'll be very happy. And with this, I'll thank you very much for your attention, and I'm happy to take more questions. If there are some.
So maybe we can also, we'll be all walking back the next talks in CCN. So any other questions, maybe you can talk to Mary-Lou on the way.
Yes.
All right, thank you again so much.
Hey everyone, welcome to our last session of the day. I'm really happy to announce Frank, who is a postdoc here in CCB in my group, actually. And so he is going to talk today about some neural architecture search, which at least one person was interested in the other day. And just generally applying deep learning to genomics. So he's done some really great work on deep learning methods development in genomics, and sort of the unique challenges that genomics have, which we haven't heard a ton about up till now. So I'm hoping this will be a cool, slightly different perspective on a new science we haven't talked as much about with all these astrophysics-y things we've been doing. And Frank has done a ton of work in this space. So this should be really great. And yeah, go ahead.
Yeah, thanks. I guess I'll take off my mask. Yeah, so as Natalie mentioned today, I will probably talk a bit different application-wise. It's quite different in terms of computational genomics and computational biology. But I hope that the underlying methods will be similar and familiar enough. But please do feel free to stop me at any point if you have any questions. So the outline of today's talk is I will first introduce some basics of deep learning applications in genomics, and specifically using neural architecture search on NAS. As I understand, we have a pretty diverse audience here, so I want to make sure that we have an overview of what's happening in general for applying deep learning in genomics. And in the next two sessions, so I will specifically tell you two projects where we applied NAS techniques to model genome editing biotechnologies using CRISPR-Cas9. So without further ado, let's first look at the modern genomics, right? So how many of you are familiar with the concept of genome-wide association studies? So not many, okay. But this is really a classic example of GWAS, or genome-wide association studies. So basically, here we are measuring different individuals' height together with their genotypes, right? So if we collect enough samples for those pairs of height and genotypes, we can run a very simple correlation analysis. So in this hypothetical example here, you can see this RS123. That basically means a specific location in your genome. And at this particular location, different people have different alleles, we call it, which is really just a ACGT, one of those 4 DNA letters. When we do this correlation analysis, we will see that the number of A alleles in this particular location will increase your height by about 5 centimeters, right? So if you have 2 A alleles compared to people who have 2 G alleles, then your genetically will be higher, right? So as you can imagine that this simple correlation analysis, underlying it is actually a large cohort of people who have all been genotyped. We know their genome sequences, and also we know some phenotypical variations. So this is what I mean by genomics is data-driven, because we really have these large collections of different types of data. And since the invention of GWAS, nowadays we have really been able to do this uniformly across the genome for quite a number of human diseases. So this is probably too small to read, but each of these is a different type of disease, such as a cardiovascular disease or autoimmune diseases. And then on this, each of those bars are one of the chromosomes in the human genome. And we can see that in each of those chromosomes, we have thousands of significant associations between those number of allele counts to different types of disease and the phenotypical variations. So as I mentioned, this is underlying this is a tremendously amount of data, both for phenotypical variations and also for thousands of people's genome sequences. And on the other hand, we not only measure the variations on the DNA space, we also look at the molecular variations. And here I'm using single cell sequencing technologies just as one specific example. So since the first invention of sequencing a single human cell in probably like 10 years ago, so every other years, we will have a new biotechnology that can help us sequence more modalities within the single cell. So in computational biology, this really enables us to look at and study things that has not been possible to study before, because now we have those fast generations of biotechnology that can profile different dimensionalities in a single cell. So I hope this one is probably not news to this audience. Basically, we have this fast evolution of machine learning methods. On the other hand, I'm just here using convolutional neural networks and graph neural networks as 2 examples, right? So over the years, CNN gains a lot of popularity, but geometric deep learning is also beginning to gain momentum. So next, we will look at a few of those applications of the deep learning methods in 2 types of genomics applications, right? So remember that genomics has so much data, so it's a perfect use case to apply the deep learning methods. So in the first type of those applications, which I call it as a sequence to molecule predictions, where in a general framework, we basically just take the raw DNA sequences and one hot encode that into a 4x(n) matrix. And then
We don't know what one hot encoding is. I don't know if we know what one hot encoding is.
Yeah, so one hot encoding is basically you take ACGT, those 4 DNA letters as 4 channels. So whenever you see one of those letters, this is 1. So the rest of the channels will be 0. you have this matrix that corresponds to a specific chunk of DNA sequence. So this is very similar to an image. We can apply those 1D convolutions to find those local patterns along these DNA sequences, and then after that, use some hidden layers to study the interactions of those what we call as motifs, but really they're just local patterns in your DNA sequences. And using this technique, we can predict a range of different molecular variations, such as a protein binding site for this DNA sequence, gene expression level for this DNA sequence, or methylation and splicing. So those are different molecular phenotypes that we can all try to predict using this given DNA sequence.
Sorry,
yep.
Here you have labels, or you are just.
Yeah, great. Yeah, yes, we have labels, and that's precisely where I'm trying to go here. So basically, we have, as I mentioned, the single cell scenario, right? So we can use experiments to profile what those biochemical markers look like along this whole genome. So imagine this line here. Each of that is a genome, and then by calling some of the height of those basically corresponds to the signal intensity for this given chunk of DNA. So what we're trying to do is we input all these DNA sequences for this chunk, and then we'll try to predict the height of those experimental profilings. And this is precisely one of the very earliest application of multitasking deep convolutional neural networks that are developing in our group back in 2015. So we try to take a DNA sequence and try to predict the signal intensities, which corresponds to a range of biochemical markers in that part of the DNA. So of course, you can also, using the same type of input-output, you can also try to vary the neural network's architecture. So as I just mentioned, in the very first early work, we use convolution, pooling, and dense. And in the follow-up work, basically another group added these recurrent, bidirectional recurrent layers after these convolutional layers. And this also has a very interesting biological implications, because we know that DNAs are usually read by some proteins. And then when the proteins does that, it actually do this in a linear sequential way. So by incorporating those bidirectional LSTM layers, it actually better captures a lot of the data generating mechanisms. And they were indeed able to show that this updated architecture was able to perform better than the original one. So in the second type of deep learning models, we're not using the sequences. We're not restricted to the sequences, but we're more interested in predicting those molecule to phenotype predictions. So for example, here, we're trying to predict the drug and the DNA interactions for the cancer cell lines. So on the left, we have a similar to what we have before for the sequence. It's the mutations in those different cancers. And on the right, we have a fingerprint for those different tumor drugs. So by considering those two jointly, we can try to make an interpretable model that predicts the growth effects of a different tumor drugs. And interestingly, those neural network architectures are actually, you might also already noticed this funny looking architecture. So this architecture is actually inspired by existing biological knowledge. So each of those sparsification is constrained by prior existing biology ontologies. So we can also do this to predict the cancer types for primary versus metastatic tumor in real patients. So previously it's in cell lines, it's like on a plate. Now we're looking at real patients. And similarly, we start with mutations that are specific to any patient and try to predict whether this particular patient's tumor is primary tumor or metastatic tumor. So just for the reference, it is the metastatic tumor that kills most of the patients. So those are we want to distinguish from the good tumor, relatively good tumors from the bad tumors by just looking at their mutation signatures. So now this really, I want to wrap this up by looking at the challenges and opportunities for applying AI methods in medicine. So on the left side, as we just discussed earlier, there's a rapid accumulation of big data in this biological domain for both on the DNA side and also for different molecular profilings. And something that we didn't get to cover is those clinical data, such as the electronic health records or medical imaging. But on the right hand, we also have a fast evolution of more powerful cutting edge deep learning methods. So how to use these new generations of methods to model this large amount of data remains a challenge for applying such techniques. So this is precisely where we developed neural architecture search methods that is specifically for genomics applications. So this whole architecture search method is powered by a reinforcement learning agent, which is coded as a recurrent neural network. So before I go to the details, I just want to tell you that this search is incredibly efficient, and we can finish a searching a large model space in a very short time period of only 72 GPU hours. So next, I will just tell a bit more about how NAS works, right? So suppose we try to learn a function that maps your input x to y, right? So we can parameterize this function by a neural network. And in this case, we have two hyperparameters A, or the architectures, where it corresponds to like how many layers you have and what type of computational operations you put in each layer. And once the architecture is fixed, within each layer, we will have some trainable parameters that can be optimized by gradient descent, and those we call it as omega. So you can already see that this has a nested optimization flavor, right? So you first need to fix the architectures, and then you can use gradient descent to optimize omega. And specifically for neural networks, this we can do this in a layer by layer manner, right? So for example, if we're trying to determine what computational operations to include in the third layer, A2, so intuitively that will depend on the previous two layers, right? So mathematically, this is a conditional probability of the Tth layer conditioned on all the previous layers. And in this toy example here, so suppose the previous two layers are already convolutional layers, then for the A2 layer, you probably want a pooling layer. So this conditional probability is being parameterized by this recurrent neural network so that you can capture all those autoregressive characteristics between different layers. Finally, how do we train this conditional probability generated by sigma theta? We can do this using a very classic reinforcement learning method called reinforce. So basically, we want to parameterize the likelihood of selecting a specific set of architectures by this pi here, and then use the reward multiply this likelihood. So the objective eventually is we want to find a region where we can sample these high reward architectures with a large likelihood. So it's very simple, but this provides a general framework that we can build on top of it. For example, we can now, between those conditional probabilities, we can now insert residual connections to make it more complex and more powerful as well. But yeah, sorry.
Where is the reinforcement learning coming in?
It's the reward part.
So is AK like some module or something, and then that would be your action, I guess, choosing one of those.
Yeah, so in this case, the actions are all chosen from the model search space, right? So it's the A is also your actions. And then the reward is the usually just the validation accuracy, right? So you want to optimize the likelihood so that if you want to move the gradients to a region where the reward is high and move away from regions where the reward is negative or low. Okay, so I guess one more comment is this is very classic, but also we find it very useful empirically. But apparently, you can also use other reinforcement learning techniques, such as clipping the rewards and use a proximal optimization, right? So in reality, this search algorithm really depends on how efficiently you can sample and determine the rewards. So another part that I didn't get to cover today is how you actually evaluate this reward. And the reason why we can do this so efficiently is actually through this weight sharing scheme, so that we don't need to train each individual neural network to full convergence. Okay, so now we have this method, we can apply this to see if we can actually improve upon the upon application in the genomics domain. So here we're applying this method back to this classic multitasking deep convolutional neural network task, which is called a DeepC that I mentioned earlier. So if you still remember that, we're trying to use a chunk of DNA and try to predict 900 biochemical markers through this multitasking learning framework. So to compare against that, we first sample this, we define a model search space and uniformly sample architectures from the same model space, and to form this best performing randomly sampled model architecture called Amber base. So in this architecture, different operations are color coded. So because you are uniformly sampling those computational operations, you can see this architecture is fairly colorful, right? So it tend to choose different computational operations. And compare that to our search model, which we denote as Amber-seq, it really just prefer to use 3 of those computational operations. So which is the convolution with kernel size 8, 4, and finish that with the max pooling. So interestingly, the choices of these computational operations is highly aligned with the choices made by the human experts in the original implementation of DeepC. While at the same time, we were able to outperform the one designed by human experts by a pretty large margin, while using a lot fewer trainable parameters. So this demonstrates that the search model is both accurate and parameter efficient. So Amber is a software to perform NAS. It's publicly available and reusable across biological domains. So for example, as I mentioned earlier, in type Y models, we're trying to use a sequence as input and try to predict a range of biochemical markers. We can just follow this very similar logics, even though the biological applications could be totally different. Yeah.
So I get what you did here. How is it like? I mean, in like these days, there are like so many neural architecture search methods, right? Like, do you have like some sort of comparison, like Amber versus?
Yeah, I'll get to that later.
Okay.
Yeah. So, but before that, I want to emphasize that this framework is reusable across different biological domains. So as I mentioned here, we're trying to predict biochemical markers, and then in the later part of my today's talk, I'll tell you how this can be applied to CRISPR-Cas9.
The question.
Yep.
What is specific to biologic domains in Amber? Is it just that it sort of expects a sequence input?
Yeah, that's certainly one thing. And I'll answer that right in the next slide. So yeah. So I've also been thinking about what's so specific for applying NAS in biology, right? So one big difference is that in biology, we are using the same, we can generate the data in the same format, but they actually corresponds to very, very different biological factors, right? So here, what is shown here is we're sharing the same model search space, but for different biological factors. So basically, if you look at those transferrin factors, which is a specific type of proteins that binds to DNAs, it really tends to use this convolutional layer with a larger kernel size of 20, right? So versus this green band, which is a histone, this is a chemical modification happening on DNA and like the proteins that wrap around DNAs. So they actually prefer to use a smaller kernel size. And we know that this is actually interesting because transferrin factors tends to have a larger motif versus histone marks will have a smaller one. So the different preference of the architectures actually can correspond to some of this underlying biological mechanisms. And another interesting phenomena is that we usually see those divergence of architecture preferences in the early layers, right? So if you look at the first 3 layers, it tend to be very factor specific. But by the end of this side, we're going to the output, then you can see all the bands starts to converge, and they're really just using the most efficient way architecture, regardless of the biological factors. So this is really very different because in computer vision, you're trying to find this foundation model that can be applied and just by fine tuning to different applications versus in genomics, because we have such diverse factors, proteins in the genome. Each of them will need a specific architecture to accommodate the specific needs of this data. So if there are no questions, I'll move on.
Sorry, I don't really understand how is this called, alluvial plot? Like what? So the width means like.
Yeah. So the width actually means the transition probabilities, right? So remember that when I talk about the NAS basics, we're really just trying to learn this conditional probabilities, and the band will corresponds how the transition probabilities across different layers.
So, but you're saying that different biological factors map to different neural network architectures. Mm-hmm. How is the neural network architecture represented here? So,
yeah. So basically, if you look at this red band, which is a specific biological factor, so the optimal architecture will follow this the thickest red band, versus another one, this green one, will choose different ones, or the yellow one, right? So yellow one will use average pooling, versus the red one will use max pooling for this specific layer.
Gotcha. So you construct those widths because you search.
Yeah.
Okay.
Yeah. So because we search for different biological factors, and apparently this there's a problem of computational cost here. So in the future, we'll move forward to apply these training-free NAS techniques so that we don't need to spend so much time searching for best architectures across a number of biological factors. But the use of NAS or AMBER as a software is not just for on the DNA sequences. So an independent group from CMU actually benchmarked this on another one-dimensional data called electrocardiograms, or ECG. So ECG is a medical technique that can profile your heart rate and then use that to help diagnose a range of cardiovascular disease. So they use publicly available data, and the data looks like this. So basically, we have around 60 seconds of those 1D signal sampling. And we're trying to predict one of those 4 classes based on this 60 seconds recording, whether this is normal, disease, other, or just purely random noise. So the authors applied several NAS methods on using this same publicly available data, and also compare that to a randomly wired wide residual neural network. So we can see that for the ECG dataset, Amber really works the best out of the box. And the authors was also able to reproduce some of the results in the DeepSea task, which I just mentioned to you earlier. And in both cases, Amber is really working very well compared to not only the competing NAS methods, but also the random wiring baselines. So Amber is also very easy to use. So basically, this is a script that taken from the benchmarking paper. And you just need to import and set up the model space and then write your own functions to read in your training and validation testing data and hit a run button. And since the new release, this 70 lines of run configurations can also be pickled, so you just need to reload it to just make the use of Amber even easier. So next I will tell you a little bit more about our own applications of Amber in the field of genome editing. So in the first part, I will tell you how a deep residual convolutional neural network can be used to predict the editing outcomes for CRISPR-Cas9, which is the most popular genome editing tools out there. And this work is done by Victoria, one of my very prominent students. So CRISPR-Cas9 is a revolutionary biotechnology that can edit your genome. So it works by this. So Cas9 itself is an enzyme, and it can be charged by a guide RNA. And this guide RNA is you can program it for it to be complementary to a specific target in your human genome. So when you transfect those guide RNA and the enzyme complex into cells, this enzyme will find the target that is complementary to your programmed guide RNA and perform a cut. So it has long been thought that the repairs of those double-strand break induced by this cut of Cas9 is purely random. So until recently, people start to realize that they're actually predictable. So what I mean by Cas9 editing outcomes. So let's look at this specific example here. So suppose we are programming the Cas9 to target this part, this set of the sequence, and the Cas9 will precisely make a cut this dashed line here. So after the cut, there's a DNA repair pathway in the cells that will come and repair this double-strand break. And around 60% of the time, after the repair of this break, we will see additional A being inserted right after the cut site. And about 4% of the time, we'll see a deletion of 3 nucleotides that looks like this. So this 60% and 4% is reproducible no matter how many times you do the same experiment, as long as you're targeting this specific set of sequence. So this is a perfect scenario to perform machine learning, because we know that the input is this targeting sequence, and we try to predict what's the percentages associated with this sequence. So there indeed exists a few number of machine learning methods that can, yeah.
I didn't completely get like the setup here. So we perform some cutting on the original sequence, and then when this gets repaired, we see these changes.
Yes.
Okay.
And these changes are associated with the original sequence, so that we can use the original sequence to try to predict the repair outcomes.
And we don't know like why these particular sequences. Like
we know some biological mechanisms. So for example, this one base pair insertion is mostly regulated by a particular repair enzyme. that prefers to bind certain sequences but not the others. So there are some reasoning behind why we can predict this.
Okay.
Okay, so there exist three machine learning methods in this domain to try to use this original sequence and try to predict the outcomes. So they use different machine learning methods. So for example, the very first work uses artificial neural networks with the nearest neighbors, and follow-up works using gradient boosting machines or logistic regressions. But the common feature of all those three works is that they first use feature engineering to derive informative features from this input DNA sequence. And then they have to tune their model parameters before the model can be deployed. So we reason that by utilizing their data, published data, we can actually do better by employing both the deep CNN and the technique of NAS. So the objective for this project is to first want to create a model and see if that can perform better than the previous ones, and then apply that to genomic variations in patients. So in the first step, we try to create a new model called Croton, where we take these one-hot encoded DNA sequences and try to predict 6 different outcomes. Again, this is a multitasking learning framework. So compared to the existing methods, so if we use a deep convolutional neural network, we can bypass this feature engineering step and directly take the raw sequences as input, because we know that CNN is excellent at learning patterns and features from those textual data. And we can, if we further couple that with Amber or NAS, we can even further skip this model engineering. So creating this end-to-end model data acquisition to model deployment pipeline. So that's precisely what we did. So in the first step, we want to evaluate whether this model search step actually gives us better performance than just randomly sampling from the same model space. So we see that compared to these sampled architectures, our search model is indeed performing better than almost all of these sampled CNNs from the same model space. So the reason why that's the case is because, again, we prefer to find the specific computation operations among these candidate operations. And in this specific case, we're seeing that the dilated convolution with a kernel size of 8 is being almost universally preferred than the rest of these convolution operations. And again, this is biologically meaningful because the repairs are dependent on some complementary patterns that are far away. So by using this dilated convolution, we can actually increase the receptive field to capture those similarities that are not immediately in the local neighborhood. So now, yep.
The Amber can change the number of layers as well, right? Or do you fix the number of layers you want?
Yeah, that's a great question. So right now we set a maximum number that is determined by the model space, and a layer can be removed by choosing this identity layer. So if you have this identity layer, that will be removed. But that is mostly functions through this validation accuracy as your reward. So if you're using too many of those complex operations, then that will hurt your validation performance, and then this will be downweighted. Okay, so now we have shown that the searched CNN indeed performs better than a randomly sampled CNN architecture. We want to compare that to this existing machine learning methods. So quite surprisingly, we were training on this forecast data set, and we showed that this, and then tested on this another Sprout data set, right? So in that way, we can really make this evaluation completely independent. And we show that in this independent data set, we were outperforming this previous two methods in Delphi and forecast. And even for this machine learning method that is specifically trained on this T-cell dataset, the Sprout dataset. So this really indicates that our automatically designed model was generalizing extremely well. That is not just works very well on this training validation dataset, but also on this different cellular context that is held out throughout this entire process. So because we didn't do any of the feature engineering, we still want to understand what are the nucleotides, what are the features that the quantum model is using to make such accurate predictions. So in order to understand this, we use a technique called in silico mutagenesis, which is essentially just a perturbation-based interpretation methods. And each time we will mutate one of those DNA bases, where we have A, C, G, and T. If we remember, for example, from A to T, how does that change our model's prediction? So if we do that for every location across this 60 base pair or 60 long vector input, you can see that the latter changes around the cut site in the middle of those 60 base pairs is the most important. And this is actually aligned with the existing biophysical studies of Cas9 enzyme. And by comparing the influence of those base pairs across different tasks, we can also start to see some interesting patterns. So for example, for one base pair insertion, it's really just utilizing a few nucleotides that are near the cutting site, versus for more complex biological outcomes, such as a frame shift, it's using a much larger window of nucleotides that are spreading across almost all 60 base pairs. So we can finally we wrap up this machine learning method by developing a Django. Let's see if we can get this to work. But a small Django application. So basically, if we import the sequence and hit predict, this will tell you the model's prediction. So just to make it a little bit user-friendly for those experimental users, because after all, we want this the people who actually perform Cas9 experiments to be able to use this. And a lot of times they don't necessarily know how to run a Python code. So now that we have a good performing machine learning model, we want to study the genetic variations that can influence the editing outcomes. Yeah.
So just to understand, in Croton, like the main kind of like advantage is this neural architecture search, right? Like that's your main contribution. Okay.
So yes, so the neural architecture search was able to give us a better performance than the other competing methods, and because the fact that we didn't use any of the feature engineering, that also gives us unbiased feature importance scores.
Okay.
Yep.
So from the previous figure, it seems that maybe an attention mechanism will enhance the performance because it will focus in the middle.
Right, exactly. So yeah, that's a very good point. So basically, if we just want to predict one base pair insertion, we don't actually need all those 60 base pairs. All we need is just this center part. But on the other hand, for this more complex frame shift, then we are actually using a lot more sequences. And you're right, if we use this attention mechanism, actually that will help us to find this distant, the similarities that are quite far away. Yeah. Okay, so genetic variation. Yeah, go ahead.
You have like a confidence score or like error bars on the predictions?
Yeah, that's a great point. I don't think we have one, but I love to have that because I think the uncertainty for deep learning methods, right, at least it's very important for biological applications, but I don't see many of that given yet. Yeah. So okay, genomic variations. I assume like a lot of you still are not so familiar with the concept of genomic variations of why Cas9 is important to that. So just to get us on the same page, CRISPR-Cas9 has been used to treat multiple diseases in ongoing clinical trials. And they can be classified roughly in two routes. In the first one, we can use that to treat for antiviral therapies. So for example, we know that HIV enters the human cells through a protein called CCR5. So if we can knock out, basically destroy that CCR5 gene, then HIV will have no way to enter human cells. And this is why we can use Cas9 for antiviral therapies. And on the other hand, perhaps more promising is to treat cancers. So basically, cancers have a mechanism to secrete specific signal proteins to repress humans' immune cells. So if we can extract some of those immune cells from the patient and then edit out this immune blockade gene that suppresses the immune cell, and then inject those edited cells back to the patient, then those edited immune cells will act as patient-specific weapons to target the tumor cells and destroy them. So this has been used in this ongoing clinical trial to treat lung cancer patients. Yep.
So do we have like antivirals that use these like CRISPR-based methods?
That's a great point. So a few years ago, it's in a completely unethical application. Someone actually tried to edit out CCR5 in embryonic stem cells. So basically, the newborn babies will be born immune to HIV. But that's completely unethical. So don't do that. But there are some other ongoing efforts that are ethical, but they're not as nearly as far as these cancer immunotherapies.
Is there some particular reason? Like,
yeah, so mostly because these cancer immunotherapies, you can extract the cells, edit that, and then inject back. So at this step, right, you can do a lot of lab work for those cells to make sure that they are safe and effective. Okay, so at this point, I hope that you at least get a sense that CRISPR-Cas9 can be used and actually is already being used in some ongoing clinical trials to treat human disease. But why is this single nucleotide variations or genomic variations so important? So the reason is that the human genome is actually loaded with different genetic variations. I guess on the high level, we all know that everyone is different. And so everyone's genome is also different on specific locations. And in this specific example, what we're seeing here is you have the reference genome. You will have a 90% one base pair insertion probability, and only 10% of the cells will not generate one base pair insertion probability. And in this case, we wanted the insertion to destroy the gene, right? So 90% of the time, you will have a success edit. Versus if you in these alternative alleles, basically it's the allele that is seen less than 50% in the human population, then this allele could really change your editing probabilities from 90% to 40%. Then this targeted therapy for someone with this C allele could be a huge success with 90% of the chance to destroy this gene versus for anyone with this A allele is not working extremely well. And this will create this differing gene inactivation efficacy and eventually lead to this difference in the cell-based therapy efficacy. So we run Croton uniformly across the genome and then specifically picked a few genes that has been utilized in clinical trials or has the potential to be used. And we see that for each of those genes, those natural occurring genetic variations, like the one that I just showed you, C2A mutation, can actually significantly alter the predicted editing outcomes as large as 30%. So to make things even worse, some of those variants can actually be linked to specific ethnicities and genetic backgrounds. So for example, here we are looking at a particular gene called FGFR3, which is a biomarker for several tumors. And suppose we want to edit this gene using a PAM ID, which is a specific location in this gene called 147. So if you have this reference allele, which is like seen over 50% in this in human population, so the knockout efficiency is actually pretty high. It's over 80%. But if you have this alternative allele of C in this particular location, that will significantly decrease the knockout efficiency by 20%. So you only have 60% of this success to edit out this gene. And in this particular case, the C allele is actually very, very frequent in this African population. So almost one out of three people with African genetic background will actually carry this C allele instead of the T allele. So if we're actually targeting this region in the clinical trials, this will not be a very good choice, because for anyone who carries this C allele, it will significantly decrease the efficacy. So you might think this is still far away from clinicals or in human trials. So next I'm going to show this gene, which is the one used in ongoing clinical trials called PDCD1 to treat lung cancer patients. So this is the gene that we're trying to target. So they have different exons and introns, basically the structure of the gene. And then each column is one potential target site for CRISPR-Cas9. So you might not be able to see it very clearly, but for each column here, we have a small little horizontal bar here that represents the reference allele prediction. And then each of the dots is actually the prediction when you alter one of those SNVs, single nucleotide variations. So the first thing is I hope you can appreciate that by considering those natural occurring genetic variations, we're actually introducing a large amount of variations on top of those reference predictions. So meaning that once you consider those differences in everyone's genome, the predicted efficacy could actually be varied a lot. And in particular, I want to draw your attention to those two orange boxes. So those two orange boxes are being used in this ongoing clinical trial. And for at least one of them, right here, we can see that one single nucleotide variations can dramatically decrease the predicted efficiency of one base pair insertion, which means that for anyone who carries this genetic variation, his or her outcomes will be dramatically different from the rest of the cohort, again, which is something that we don't want. And to facilitate the use of this in a clinical and experimental community, we make a database called CrotonDB that can systematically query these different genetic variations and target sites. And again, here I'm showing that another high impact journal paper in Cell, where the authors try to knock down CD33. Again, they have an even larger effect size for a particular SNV with as large as 40%. So I guess we can conclude with that this effect is actually quite ubiquitous, and it's important to actually consider those SNVs when designing clinically used guide RNA targets for CRISPR-Cas9. So for this part, I will just summarize as we developed this fully automated and state-of-the-art performance CRISPR-Cas9 editing outcome predictor called Croton. And because it's fully automated and we don't rely on any feature engineering and prior knowledge, we can use it to unbiasedly estimate the genetic variations effects. And we show that indeed by considering those effects, we can actually give meaningful and insights to guide the clinical use of CRISPR-Cas9. Okay, so next part. So then in this part, I'll describe another important step for CRISPR-Cas9, which is the off-targeting effects. So off-targeting effects, and I want to acknowledge Adam, who is my colleague at the Simons Foundation, and also who has contributed a lot to the biophysics side of the story. So CRISPR-Cas9 off-target effects means that
I just want to clarify like what you did like previously just before we get into this. So we have this model that tells us like if I edit out some target sequence, I mean if I use CRISPR on if I cut out some part of a target sequence, what would be the resulting repairs done, right? And now you use this to analyze the variants, like so if I change like one nucleotide to another, how the effects would change.
Yes.
Okay.
Yes. And this is particularly useful in this clinical studies because everyone's genome is different.
Okay. So this model now tells you if I change one nucleotide, like this is how the repairs are going to be different.
Yes.
Okay, good.
Yeah. So I guess following on that, we've seen a lot of analysis on how this DNA's cut can be repaired. And now we're moving we're taking one step back and see which of those genomic locations will actually be cut. That happens before the repair, right? So this is denoted as off-targeting effects, where those genomic sequences that are similar to your programmed guide RNA but not identical will be cut by mistake, generating these off-target effects. And this is really a serious problem, especially if we want to use that for therapeutics, because even a very low frequency of the cells are cut by mistake. Like even a single cell is cut by mistake and become cancerous. In the long run, that one single cell can expand and replicate itself over the many times and years to come, and then eventually the patient will develop a very severe cancer. So we want to minimize the off-targeting effects. But that's not always easy because, for example, if you look at this figure here, this is experimental data from a few years ago. What we're trying to target to edit is in this green bar. But all those red bars will also be edited just because they bear some similarities to this green bar, right? So it's really important to understand which of those red bars will be edited besides this green one and how to minimize that. So for that, we need to understand Cas9 as an enzyme, its kinetics. So how fast is going to cut the on-target sites versus how fast it's going to target the off-target sites. But the existing off-target data, as the one that I just showed you earlier, cannot actually profile the kinetic rates, the time-resolved kinetic rates. So they usually just use high-throughput sequencing reads as the surrogate, and that cannot distinguish the enzyme-specific characteristics to, for example, how long you expose the enzyme to your DNA substrate and the genetic context. And if we're trying to build this kinetic model, right? So, for example, this biophysical model that uses kinetic theories to transit between different states, we are encountering some other difficulties, such as we don't know how many states are valid during this binding and cleaving process, and which of the transition rates are the fastest or slowest. So we can try to address this challenge by using a specific formula. Yep.
I think I'm just like a little bit unfamiliar with CRISPR. Can you explain what is like the role of the gRNA and Cas9 in this whole process?
Yeah. So I guess that for that we need to go back a little bit. So Cas9 is this protein, right? The protein will cut DNAs. It's like a scissors. It just cuts the DNA. And then this protein can be charged with a programmable guide RNA, which is a 20 base pair, right? So you can ask some biotech companies to synthesize this guide RNA, right? The synthesized guide RNA will be complementary to a specific region in your genome. That is your target region.
Okay.
And then Cas9, once it's charged with this guide RNA, is called the RNG complex. So basically means the protein with this RNA is a complex. And then you transfect that to the cells, and then Cas9 will search along the genome to find the target region that are similar to your programmed guide RNA and perform the cut.
So the reason why we have these off-target events is because our gRNA is like making mistakes, like it's going to, it's binding with the wrong targets.
Yeah.
Okay.
Yeah. So across the genome, there will be places that are very similar to your gRNAs, although not identical. So if it's identical, it's not off target, it's on target. We were trying to edit that place, but even sometimes this is not 100% identical. It will also be edited by mistake. And the important part is not just where will be edited, but how fast different places will be edited. So that's why it's so essential to understand the kinetics for this process.
So on targets, the correct sequences are they are operated on much faster.
Yes.
Is that the intuition?
Yes.
Okay.
But not. We actually see some cases where the mutations can operate almost as fast as the on target.
Okay.
So that's also something that we're trying to delineate.
Because they're like biochemically complementary, right? The guide RNA strand, so it should biochemically attach much better to the closest match.
Right.
Is the mechanism, right, for speed?
Yeah. Yep. Okay. Yeah. So I hope that we're clear that why understanding this kinetics is so important. And by the way, it's the great question. Just feel free to ask anything if you lost at any point. So biophysically, we can use a master equation to model these transitions between states. And in this particular case, we're modeling the Cas9 cutting as a first order kinetic reaction. And we assume there are 4 different states, right? So there's a free enzyme that are floating around, and it starts to bind in the first initial step of the guide RNA and the DNA complex. Then it goes on to this intermediate R loop, and then finally close R loop. Then Cas9 will perform the cut. So biophysically, we can use this master equation to describe this whole system. And to find this actual effective cleavage rate, chemists King and Altman around 50 years ago discovered that they can use a partition function like term to describe the steady state occupancy by multiplying different vertices. And once we have this long steady state occupancy probability, we can multiply this by this cut rate so that we can get this effective cleavage rate. And there are 2 parts of this process that can be modeled by a specific type of neural network called kinetics informed neural networks, which I will describe in detail next. So the first part is finding the sequence determinants of those different kinetic rates. So for example, for K on, it depends on the first 4 nucleotides, and K off may depend on some other sequences along this 20 base pair sequence. And we're modeling this sequence dependency by a convolutional neural network. And in the second part, we want to understand how those how those rates are being transitioned among each other. So for that, we can use a graph to describe this. So in this particular case, it's just really three states. It's an enzyme substrate complex, enzyme product complex, and goes back to enzyme. But in reality, we don't know how many states are there and which of the states transitions to which. So for that, we can use this King-Altman theory to convert this graph into a softmax layer that is right here. And then we can use this final catalyzed state and multiply that by the K-cat as the effective kinetic rate. So apparently there are several choices that we need to make in order to implement a kinetically informed neural network. So we can do this again through the means of NAS. So in this particular case, we can first generate a population of those king models and then evaluate their reward by looking at this validation Pearson correlation from a predicted rate and observed rate. And some of those better architectures will survive through this selection that goes to the probabilistic model distribution and generate a posterior probability for your models. Then you can sample from this model posterior to generate a new population, and these iterations just goes for a loop. And of course, we want to benchmark if this probabilistic genetic algorithm actually works. So to do that, we first simulated kinetics data and then apply this framework. And we see that on this x-axis is the number of generations or the time of training. We see that indeed we get better and better models over time by updating this model of posterior probability. And eventually we can arrive at a very good model that captures the underlying ground truth. Versus if we disable the posterior update of model distribution, over time we will also be able to find better models just by random chance. But you can see the performance difference is quite dramatic. And because this is synthetic data, we can also compare the posterior model distribution to the ground truth of physical parameters that are actually we use to generate this simulated data. And indeed, we see that this whole process was able to capture this model generation, data generating process very accurately. So these dashed lines in the middle are the ground truth values, and the blue bars are this posterior distribution. We saw that they are almost perfectly aligned with the ground truth. So now this gives us faith that we can apply this framework to actually model the real Cas9 kinetic data. And the data we took from a recent Nature Biotech paper where what they did is they performed this massively parallel kinetic profiling for CRISPR-Cas9, where at each time point they try to get a sample of this DNAs and measure how many of that is being cut and how many is not being cut. And then they can feed an exponential decay function to measure the decay rate, which is the effective cleavage rate that we're trying to predict. So before that, this again is a perfect case for machine learning. We have an input, which is this guide array and this target with some mismatches. And we have this cleavage rate as the exponential fit. We don't apply this interpreter model. We just use a regular convolutional neural network and try to predict this exponential fit. So here, again, this x-axis is number of steps or like number of, or you can think of this as a surrogate for time. We can see over time, indeed, we can search better and better CNNs to model this data. And the best performance is shown here. We have a pretty good correlation of a Pearson correlation of 0.88 from the observed rate and our predicted rate. So next we apply the same process using the same features and outputs, but use this kinetically informed neural network. So you can see that this is very similar to this simulated case where over time we were able to find better and better models. And in this case, the test time performance is actually around 86. So compared to this CNN model, we are indeed losing a little bit of power, but considering this interpretability, it's actually doing fairly well. And most importantly, things is interpretable and physical, right? So first we look at the posterior model distributions, and we can understand which are the sequence determinants for each of those kinetic rates. So for example, KIO means the kinetic rate of transitioning from intermediate state to the open R loop state. And we see that those the sequence determinants are actually starting from the third nucleotide, versus for the other two kinetic rates that are intermediate to close or close back to intermediate, they actually depend on quite different sequence determinants, like on the 16th nucleotide or on the 12th nucleotide.
I have a question here.
Sure.
So you have a set of ODs, right? How you know that like the method is identifying the truth, like if it is identifiable, you know?
Wait, say that again.
If the model is identifiable, like if you simulate the system with para rates, you know how you know if the method extract the truth.
Yeah. So in this case, you're right. So basically, in this case, we don't know the ground truth. We're exploring this Cas9 because no one really know what's the ground truth in this case. And the reason why we feel comfortable doing this is because in the synthetic data we're able to recover the true rates so well.
So just to understand this, your network like predicts like the different rates, like the constants k that you are showing.
Yep.
And that governs like the dynamics of your like how much of each reactant is consumed. And so you actually don't have access to the rates themselves. You only have access to like the time evolution of the different reactants.
Yep.
But okay, so you can differentiate through everything. That's like the
yes. So we don't really know the intermediate rates. All we know is the final like effective cleavage rate. You're right. Yes. Okay. And more importantly, we want to show that the learned kinetic rates are actually physical. They have a unit of 1/per second, and as you mentioned, we can actually learn those intermediate rates as a bonus point. And just to demonstrate that this is actually correct, so my collaborator Adam plugged in those learned kinetic rates and run his Monte Carlo physical simulations. So basically, if this is the actual rate, does this generate the data that are similar to what we saw? And it turns out it's indeed the case. So we plugged in the learned kinetic rates into the simulation. We can get a log exponential decay that are just similar to what we experimentally measure, and we can also observe the state occupancy over time. So we can see that the fitted effective cleavage rate is highly concordant with our predictions. So finally, I want to go back to where we started. It's off-targeting effect predictions. So at the end of the day, we want to be able to distinguish which of those places in the genome will be edited versus which will be not. So in this case, again, we are using the test data set from this, actually, where this figure comes from, called guide-seq. So it's important to know that these guide-seq data sets are actually generated in living cells, or in jargon, we call it in vivo, versus our training data, because we want to measure these Cas9 enzymes intrinsic characteristics. They're actually performed out of the living cells. or we call that in vitro. So that really tells us like we are using different experimental approaches and they're done in different cellular contexts. So this test data set is really, really challenging. And here the task is that we want to predict which of those sequences will actually be off-target edited versus some of the sequences that are within the same timing distance, but they're not edited. So that's the classification problem. So we applied this biophysics interpretable neural network and the CNN. Remember, we have raw Amber on both of that to this task, and then compare both of them across a set of different baselines on this held out test data set. And surprisingly, we see that this interpretable mechanistic model actually performs much better, not just to other baselines, but also actually much better than this CNNs. And we speculate this is because in this kinetic interpretable neural networks, we inject such strong biophysical priors that when you test on this out-of-domain testing data sets, they actually performs better than a regular like non-interpretable CNN. And finally, we can look at just this off-target edited size. And not all of them are off-target edited at the same level. Some will be edited more than the others. And these are represented by different number of reads in this coming off the experiment. So for the reads that are like for 2000 to 5000, indeed, we are predicting that to have a very large cleavage rate versus for the off-target editing sites that with only 0 to 5 number of reads, they are indeed also predicted with a much lower cleavage rate. And this is true across all 4 different experimental approaches conducted in different cellular contexts. So this tells us that we are not only able to make this distinction between 0 and 1, but even with the positive classes, our cleavage rate prediction can actually tell you which one of them is more edited than the others.
Sorry, I have a question. Like, so the Hamming distance is just if the letter was different, okay? And if you have a sequence, have you tried like to use any other, I don't know, like identity by descent or some other distance that?
Yeah, so I think in this case, this construction of a testing set is actually a widely used data set previously generated by others. So in order to make fair comparisons, we're fixing that.
Makes sense.
Yeah. So I guess finally to summarize it, I present you a genetic algorithm-based neural architecture search technique that can search for this kinetically interpretable neural networks. And we show that this king can shed mechanistic insight for this Cas9 enzyme editing, and it actually outperformed, to our surprise, a lot of the state-of-the-art off-targeting predictors are based on previous machine learning methods. So to wrap up today's talk, I'll tell you a few types of deep learning applications specifically for genomics and why it's so important to develop and apply the technique of NAS in genomics, and followed by 2 specific examples that are both related to genome editing on how we can use neural architecture search to both generate accurate and interpretable and mechanistic models to understand genome editing better. And I want to thank my lab mates at CCB and Princeton University. And also I want to advertise myself. My own lab is starting this September. So if you know someone who will be interested in working and exploring deep learning in genomics and medicine, please do reach out to me. Thank you.
I just for curiosity, why is that different architectures mapped to different features? Like, someone knows it, or is most? I mean, it's super curious, right? Like,
Which part of the work are you
Like
referring?
different, like the neural architecture research, like like the alluvial plot, or I don't know how you call it, like the.
Oh, the Sankey plot.
Yeah.
The Sankey plot. Yeah.
It's just, well, it's impressive, no? It's like if the architecture have some information of the system, right?
This is the figure you're talking about, right?
Yeah.
Yes. It's not only. It's actually, yeah. It's perhaps even more impressive than you thought. So basically, we can even use a data descriptor vector to describe your different data sets, and then use that to generate a useful architecture in one shot. So basically, you can train a controller neural network, and then in the future, when you have a new data set, you can just describe your data, and then this trained controller can generate a data-specific architecture for you. And if you're interested, I think you can read this preprint. Where, yeah. So, yeah, we'll follow up on this in the future. But right now, the main limitation is because running NAS on each of those individual data sets is taking a huge amount of time. So we need to move on to these training-free NAS techniques.
Do you have an estimation of if the structure of the architecture or if the operations is more important? Because there are some works that say that even some randomly wired architectures can perform really well. But from some experiments that I ran, I saw that the top performing architectures from the INAS dataset had all of them had the same structure but different operations. So this is maybe a hint that I don't know, maybe the operations in the end are more important if you find the correct structure.
Yeah. So I think that's I think this is definitely still like an open area to explore. Specifically in biology, so we care not only about this like accuracy, but a lot of times also about the interpretability. And in these particular cases, I think in biology we already know that the motifs, which is basically these guys, right? Those are the local patterns in your DNA sequences. Some can be longer than the others. And their grammars also different based on different biological factors you are profiling. So I think the phenomena that different neural architectures will be preferred when you profile different biological factors will always remain there.
Also, did you encode the different operations as with one hot vectors?
Yes, that's what we did, and then we can actually in our paper we can even analyze the embedding, the learned embedding for different operations, which is quite interesting. So basically, the operations are one hot encoded, but we will actually learn embedding for those almost like word tokens through this architecture search. And what we were able to show is that the dilated convolution, if you do a PCA for these embedding vectors, dilated convolution lies right in between pooling operations and the vanilla convolutions, which makes sense because dilated convolutions can enlarge your receptive fields just like a pooling, but it also does convolution. And I think a lot of works in the NAS field has been focused on improving the embedding learning. So yeah, so if you have a good embedding for your operations, you can even use a very simple like Bayesian optimization to do that. Yeah.